Every day, over 2 billion square feet of glass are produced worldwide, enough to cover the entire area of New York City. But have you ever wondered where the glass you look through every day comes from? Its journey begins deep in a quarry, where pale white sand from Illinois has been waiting for millions of years. And it ends on the surface of molten tin in the form of a transparent, seamless sheet. This video will reveal all the secrets of float glass, from volcanic furnaces to laser marking. And at the end, you'll learn one thing that even the largest manufacturers keep hidden. Don't switch. It's about to get truly transparent. Before hot sand becomes a clear window, it all starts in a quarry. The main raw material for float glass is high-quality quartz sand. It must be almost perfectly pure, with a silicon dioxide content of over 99.5%. Such sand is extracted from special deposits, usually deep underground, where it has rested for millions of years in geological tranquility. One of the most valuable is Ottawa sand from Illinois, pale white, as fine as flour, and extremely pure. Quarries operate like giant anthills. Excavators clear away layers of earth, and 40-ton class dump trucks deliver the sand to crushing plants. Then comes dry screening. The sand is cleaned of stones, organic matter, and the smallest impurities. Here, up to 15% of the total volume is rejected. Because if even one crystal of impurity gets into the melt, it can distort the light in the finished glass. Besides sand, glass includes several other components. Soda ash lowers the melting temperature. It's brought from salt deposits, particularly from Wyoming, in 50-pound bags or in bulk in railroad hopper cars. Limestone stabilizes the structure. It's supplied from quarries and crushed to a dust with a diameter of less than 0.04 of an inch. Dolomite, aluminum oxide, saltpeter, and also glass waste, so-called cullet, crushed broken glass from previous batches. It helps reduce energy consumption from melting by up to 25%. After primary cleaning, all components are mixed in precise proportions, which are kept as a trade secret. A giant mixer the size of a 2-story house prepares the glass flour mixture. The finished mixture is transported to the production facility by trucks, sometimes by rail or even barges, depending on the factory's location. The storage temperature must be controlled. No moisture, no extra organic matter. The warehouse resembles a sterile grain elevator with silos of 20,000 cubic feet each. Next, the batch is automatically fed into the glass melting furnace, where in just a few minutes, everything that was just sand and dust yesterday will turn into a boiling ocean of glass. The mixture, having just completed a complex journey from the quarry to the mixer, finds itself at the heart of production, the glass melting furnace. This is a true industrial volcano, over 200 feet long, with a temperature of up to 2,900 degrees Fahrenheit in the melting center. There's no open flame here. Only walls of refractory brick heated to white hot and gas burners that maintain the temperature with degree precision. The raw material is fed automatically, precisely dosed, several tons per hour. In the first 30 or 40 feet of the furnace, melting occurs. The components melt and merge into a red-hot, viscous mass, similar to honey, but 500 times hotter. Next, the homogenization zone. The mass is mixed and matures until all bubbles, lumps, and impurities disappear. And only after this does it calmly flow onto metal. This is where the magic of float begins. In the second stage, the mass enters a bath of molten tin, heated to 1,100 degrees Fahrenheit. The glass literally floats on the metal, spreading out into a uniform ribbon. It's thanks to surface tension and the perfect flatness of the tin that a mirror-smooth surface is formed on both sides, without polishing, without presses. The thickness is controlled by stretching. Special rollers or electromagnetic fields stretch, or conversely, compress the glass ribbon. This way, you can get glass with a thickness from 1/16 to 3/4 of an inch, depending on the client's needs. The length of the tin bath is over 150 feet, and the glass slowly floats along it at a speed of up to 25 feet per minute, cooling along the way to 1000 degrees Fahrenheit. This is a very critical moment. Any skew, sharp movement, or temperature change, and the glass surface will be ruined. But even at this stage, it's not ready yet. Next, the annealing zone. The glass ribbon passes through a long tunnel where it cools by a few degrees per minute to relieve all internal stresses. If this isn't done, the glass could later crack on its own without any load. Its surface is like an ice sheet without a single scratch. If you look at an angle, you can see your own reflection, as in a mirror. The size of the sheet is impressive. Up to 10 feet wide and over 30 feet long, completely transparent. In this state, the glass enters the cutting zone. Before it's cut, a computer scanning system analyzes the entire surface, looking for microcracks, inclusions, dust, stress. Any finding, and the sheet is rejected. The rule here is, better to reject early than to have glass explode in a truck or a shop window. Cutting is not mechanical, like in the old days. Now, it's laser or roller scoring. A microblade, similar to a diamond one, makes a line, and then gentle pressure breaks the glass precisely along the trajectory. Sometimes sheets are cut immediately to order, for example, 24 by 36 inches for construction glass, or the size of a screen for a Tesla. Others go in standard formats to warehouses, where they will be stored vertically, on racks with rubber pads, so that not even a shadow of a scratch spoils the perfect shine. After cutting, the calibration stage. The sheets are checked for thickness, geometry, and straight edges. High-definition cameras scan every centimeter. Lasers analyze the angles. There are almost no human hands here, only at the final stage, when workers in gloves mark the perfect sheets. In a world where glass has perfect transparency and no visible seams, marking is its name, passport, and the master signature all in one. It is in the marking zone that each piece of glass is given its identity: where, when, by whom, and for what it was created. The marking may look modest, a small logo in the corner, but it carries dozens of parameters: manufacturer's name, type of glass, date of production, shift, line, factory, and sometimes even the batch composition. The most common marking method is laser etching. A special laser vaporizes microscopic dots on the glass surface, creating a wear-resistant, matte inscription. It's unnoticeable from a distance, but easily readable up close. The font thickness is less than 1/10 of an inch. This inscription cannot be removed without damaging the glass, which is why it's often used as an anti-vandal code in safety or tempered glass. Sandblasting engraving is used for decorative or premium glass. An abrasive is applied to the glass under pressure through a stencil, creating a raised matte mark. This is how, for example, antique mirror glass or large facade elements are marked. And there's also ceramic ink marking. This method is used before the tempering stage. A special paint with minerals is applied by a printing method, often through a stencil or with a digital printer, and then baked at a temperature of over 1100 degrees Fahrenheit. Such marking is colored, noticeable, and very durable. It doesn't wash off, doesn't rub off, doesn't fade. Marking can be both technical and brand related. For example, on the windows of elite houses, the manufacturer's logo is often left with pride, as in, yes, this is Saint Gobain, or Pilkington. In some projects, marking is even used for authenticity control. For example, glass for armored vehicles or government institutions receives a serial number and a QR code. The final stage is documentation. Each sheet gets a record in the system, like in a hospital: what kind of patient it is, when it was born, what its properties are, and where it's going. This is important because glass doesn't always go out immediately. Some batches are stored for months until their time comes. Every year, over 300 million electric motors are manufactured worldwide, from miniature ones that spin coolers in laptops to giants that power trains, factory lines, and mine elevators. And each one of them is not just a coil of wires and iron, but a complex system of dozens of precisely calibrated parts. How is the heart of a machine born? Why is winding similar to weaving, and balancing to jewelry making? And how does one spark power a rotation that will last for thousands of hours? Let's take a look behind the scenes of one of the greatest technical processes, the creation of an electric motor. Inside every electric motor is a true mechanical electrical universe. The main components of a motor are the stator, rotor, shaft, bearings, housing, as well as a cooling system and terminal box. The stator is the stationary part, located in a circle inside the housing. It's what creates the magnetic field that makes the rotor spin. Inside the stator is a core made of layers of thin electrical steel, which reduces losses from eddy currents. In the slots of the core is a winding of copper wire, connected in a special way to create a rotating magnetic field. The rotor is the moving part inside the stator. It either has its own winding or is made in the form of a squirrel cage, aluminum bars cast into a steel core, which form closed current loops. When the stator's magnetic field interacts with the rotor, it starts to rotate. The shaft is a rod that passes through the rotor and extends outside the housing. It's on this shaft that pulleys, impellers, reducers, or other drives are mounted. It transmits rotation to the mechanisms. The shaft must be precisely centered. Otherwise, the motor will vibrate and wear out quickly. Bearings, usually two, one at each end of the shaft. They ensure smooth rotation with minimal friction. For reliability, they are lubricated with special greases or are sealed. The housing protects the internal elements from dust, moisture, and mechanical damage. It often has fins for heat dissipation or even a fan. The material is cast aluminum or cast iron, depending on the power and purpose of the motor. The cooling system, most often it's simple air cooling, a fan on the shaft drives air flows through the housing. In large industrial motors, liquid cooling or external air circulation through special channels is used. The terminal box is on the outside of the housing. This is where the power cables are connected to the stator winding. Inside, contacts, clamping screws, and sometimes temperature sensors. In the depths of the factory, in a workshop that smells of varnish, metallic dust, and warm insulation, stands a giant stator. A stationary ring with slots around its circumference. This is its core, made of thin steel sheets, tightly pressed together. In each slot of this ring will lie copper wire, carefully laid, loop by loop, turn by turn, because whether the motor will rotate at all depends on this. Before starting the winding, the stator frame is thoroughly prepared. The slots are lined with special insulating liners, like nests for the wire. These are materials that withstand high temperatures, vibrations, and electrical loads. And only when they are sure that the insulation is perfect, the winding machine is started. The machine, resembling a giant spool that unwinds copper wire from a bobbin, wraps it around guides and lays it in the slots. Everything is automated, but under the supervision of a specialist. One sharp movement, and the wire could lay with a kink or snag the insulation. And that's a potential short circuit. For powerful or non-standard motors, winding is done by hand. A worker inserts the wire in a loop, pulls it through with a tool, presses it to the bottom of the slot, secures it, and tightens it. The work is similar to weaving, but with shiny copper and immense responsibility. Each coil, and there are dozens of them, must be identical, symmetrical, and correctly oriented. After the first layer of winding is completed, interphase insulation is laid, and then the second layer is placed. The wire forms closed loops, phases, which are then connected in a star or delta configuration, depending on the motor's setup. Then, the wires are secured with strings or plastic fasteners, the tension and geometry are checked, and if necessary, adjusted by hand. And finally, impregnation with varnish or epoxy resin, so that all this doesn't shift even a micron under vibration and temperature under load. If the stator is the skeleton, then the rotor is the muscle. It moves, rotates, creates torque. It's not visible when the motor is running, but it's what drives everything, from a fan to a train. At the core of the rotor is a steel shaft, long and powerful. Around it, the core is mounted. A set of thin electrical steel sheets stacked into a cylinder. The sheets have slots. These are for the conductors. This is where the most interesting part begins, creating the winding that will make the rotor come alive. One of the most common options is the squirrel cage. Aluminum or copper bars are inserted into the slots, and both ends are cast into rings, like a hoop around a cage. This creates a closed current loop. Such a design doesn't need to be connected directly. Current is induced inside automatically as soon as the motor starts. It's a simple, reliable, and mass-produced option for industry. But if the motor is more complex, more powerful, then classic windings are used. A worker manually lays copper wire in each slot, carefully tightening it, bending it at an angle. Here, symmetry, precise geometry of the turns, and perfect insulation are important. The wire must lie right, not touching the metal anywhere, not crossing over, not being too tight or too loose. A mistake, and the motor will overheat or fail. The rotor windings are then connected in a specific sequence: star, delta, or another type of connection. Everything is secured, insulated, and sometimes varnished. The insulated ends are led out to slip rings or brush assemblies, depending on the design. After this, the rotor is balanced, as it has to rotate at speeds of thousands of revolutions per minute. Any extra 100 grams on the edge, and everything will vibrate, hum, and heat up. The result? A compact, shiny cylinder with windings of copper wire or closed bars. It will be inserted into the stator, and the magic of converting electricity into motion will become possible. It all starts with checking dimensions and tolerances. The gap between the rotor and the stator, the so-called air gap, must be very small. If it's too narrow, friction will occur. If it's too wide, the magnetic field will be weak, and the motor will lose efficiency. The rotor is mounted inside the stator via bearing assemblies. Sometimes special guides or hydraulic presses are used for this. The rotor shaft must rotate perfectly straight, otherwise everything will vibrate or break down within a week. At the ends of the rotor shaft, sleeve or rolling bearings are installed. They allow the rotor to rotate without friction. The bearings are placed in so-called end shields, which are then attached to the motor housing. All surfaces are pre-lubricated with special greases to ensure durability. The ends of the stator and, if necessary, rotor windings are led out to the terminal box. Here they will be connected in the required circuit, star, delta, or another. In complex motors, temperature sensors are installed to detect overheating before a failure occurs. The motor is now assembled, stator and rotor in the housing, wires connected, bearings in place. But it's too early to start it. First, varnishing, drying, balancing, and testing. All like a ritual before the birth of a real machine's heart. In a spacious room with a specific smell of epoxy resin, the stator windings, and sometimes the rotor, are coated with electrical insulating varnish. This isn't just for dust protection. The varnish strengthens the structure, secures the wires so they don't vibrate at high speeds, and prevents moisture penetration. Application is either by dipping in a bath or by spraying. The motor is completely submerged in a tank of varnish, then removed and left to drain off the excess. Next is drying in a thermal chamber at a temperature of 250 to 300 degrees Fahrenheit. This stage resembles baking. The varnish polymerizes and forms a hard protective film. After varnishing, the most sensitive stage, the motor is installed on a balancing stand. The system is like a huge record player. The motor rotates at high speed, and sensors detect the slightest deviations. Even a few grams of excess mass on the rotor can cause vibration that will destroy the bearings, shorten the service life significantly, or even ruin the motor. To eliminate the imbalance, engineers drill microscopic holes in the heavier part of the rotor, removing excess metal. This is almost a jeweler's craft. The finished motor is sent to the test stand. Here it comes to life for the first time. It's connected to a power supply. Rotations, noise, heat, current consumption are recorded, and efficiency and power are measured. Everything is documented. The motor's passport contains dozens of parameters. If the motor passes all tests, it's packaged, a seal is applied, and an instruction manual is added. And very soon, this motor could be working on a conveyor, in an elevator, or in an electric train, wearing down metal and converting current into motion, without rest for tens of thousands of hours. Every hour, over 10,000 engines are started worldwide. But what if I told you that behind their operation lies one of the most spectacular, secretive, and precise procedures on the planet? Before you is a huge red-hot cylinder, as long as a bus and weighing as much as a small tank. It will go through the hell of presses, a ritual of grinding down to the micro-inch, and even immersion in boiling oil. This is the story of the creation of a supertanker's heart, a giant crankshaft capable of pushing 400,000 tons through the ocean. But there's one detail that isn't shown in any documentary film. Watch until the end, and you'll find out what exactly makes metal live. For such wonder parts, high-strength alloy steels are used, often with additions of chromium, molybdenum, or vanadium. They provide resistance to fatigue loads and corrosion. The steel must meet strict standards. Its chemical composition, purity, and grain size are checked. This is the heart of the future engine, so there can be no mistakes here. Crankshafts for the most powerful diesel engines are usually forged, not cast as one might think. The reason is a denser metal structure and the absence of voids or cracks. The blank is first heated in a forging furnace to 2,300 degrees Fahrenheit. Then, it is gradually shaped by giant presses that exert a force of over 50,000 psi. A huge steel cylinder, glowing orange-red as long as a bus, weighing under 60,000 pounds. It has just been taken out of the furnace. A wave of hot air emanates from it, forcing workers to keep their distance. The floor underfoot vibrates. The forging begins. This is not a hammer and anvil. This is a hydraulic press as tall as a 2-story building, which, with pressure, slowly and confidently squeezes the perfect shape of the future crankshaft out of the metal. The red-hot block is placed under the press, and with a dull thud, it compresses the steel, changing its structure. Inside, the crystalline lattice melts, becoming denser, stronger, more resistant to future loads. This is just the first strike. Then another, and another. Huge manipulator jaws turn the blank at the right angle. It is stretched, bent, compressed, all to form the basic geometry of the shaft. Journals, cheeks, counterweights. After several deformations, it is sent back to the furnace. Metal doesn't like to be rushed. If it cools, it becomes brittle. If it overheats, it loses its properties. Nearby, an operator watches every movement through protective glass. Every millimeter matters. A half-inch error can cost thousands of dollars and weeks of rework. On the screen, a temperature map of the part, the press pressure, the feed angle. After just a few cycles, the blank begins to resemble something familiar. It is still far from the finish line, but the shape gradually emerges, a huge skeleton of the future mechanism that will turn the shaft at a speed of 80 revolutions per minute and push the supertanker forward. The supertanker is an incredible 437 yards long. That's almost 4 football fields. After the final strike, the part is slowly pulled aside onto a cooling platform. Steam rises above it, and the crackling of the contracting metal can be heard. Mechanical processing still lies ahead, but already this is a crankshaft blank. The heart of an engine that will feel every wave of the ocean. After all these manipulations, a blank that has been through the hell of forging stands in the workshop. A red-hot steel bone, over 33 feet long, weighing under 25 tons. It already resembles a crankshaft, but only resembles. The surface is all in rough marks from the press. The edges are uneven, and the tolerances are far from precise. And here begins the finest, slowest part, machining. The giant part is carefully installed on a lathe the size of a bowling alley. It is clamped in jaws that can withstand pressures of thousands of psi, and rotation is started. And slowly, carefully, a cutting tool approaches the surface. The metal is turned layer by layer, no more than 0.02 inches at a time, and each of these layers is machined with surgical precision. The lathe is connected to a computer numerical control system, and it forgives no mistakes. Here, thousandths of an inch decide everything, because if the engine's rhythm is uneven, the ship won't be able to hold its course. After rough turning, they move on to milling, forming lubrication holes, making grooves, grinding bearing seats. The tools are coated with diamond dust or made of hard carbide, otherwise they simply wouldn't withstand contact with such dense steel. During processing, the shaft rotates slowly, just 2 or 3 revolutions per minute, sometimes even slower. It is lubricated with a special cooling lubricant, because without it, the tools would overheat and microcracks would appear on the surface. Each surface is checked after a pass with dial indicators and a laser measurement system. No more than 1/1000th of an inch of error. That's the tolerance for the journals that contact the bearings. Everything must be perfectly round, perfectly smooth, perfectly weighted. The crankshaft is a rotating system, and the slightest imbalance in such masses will cause vibration that will tear the engine apart from the inside. Therefore, it is placed on a special stand, sped up, and with the help of high-precision equipment, it is determined where exactly an extra 5 or 6 ounces of steel need to be removed so that the weight is distributed perfectly. After this, final grinding is required. Grinding heads are used to polish the journal surfaces to a shine. Now its dimensions can be measured not in inches, but in micro-inches, because every microscopic defect means overheating, friction, wear. Everything is recorded in a quality certificate, and if something doesn't comply, the blank is sent back to the furnace. This stage takes from several days to several weeks, depending on the shaft's size. But in the end, the output is a perfect steel giant that will rotate in the depths of the engine with a force capable of pushing hundreds of thousands of tons forward. After the crankshaft surface is polished to a shine, a mysterious, almost alchemical stage begins: heat treatment. At first glance, it's already finished, but inside, the metal is not yet what it should be. It needs to be hardened, literally and metaphorically. Because this shaft will work in hell, under loads of tens of thousands of pounds, at temperatures over 300 degrees Fahrenheit, for thousands of hours without rest. The crankshaft is placed in a huge thermal furnace. This is a steel chamber the size of a truck. The temperature gradually rises to 1,500 degrees Fahrenheit, and so the shaft bakes for several hours, sometimes up to a day. This is structure normalization. Upon heating, the steel grains expand, and the stresses that accumulated after forging and machining disappear. The internal metal becomes homogeneous, more elastic, ready for loads. After heating, the part must be hardened. The shaft is taken out and quickly cooled. This can be an oil bath, hot oil in which the steel hisses and bubbles as if boiling, or a controlled flow of air from nozzles. It all depends on the type of steel. But the essence is the same. With rapid cooling, the outer layer becomes super hard, forming a so-called hardened crust capable of resisting wear and friction. But such hardness has a side effect: brittleness. So next, tempering. The shaft is heated again, already to 1,000 degrees Fahrenheit or slightly less, and held for several hours. This restores its balance. The metal remains hard, but no longer brittle, like a well-tensioned spring. Strong, but elastic. At the end, induction hardening for the most critical zones, the necks and seating areas. They are treated with high-frequency currents. A contour coil surrounds a part of the shaft, creating local heating, followed by instantaneous cooling. This allows strengthening only those areas that receive the greatest loads, without affecting other parts. After the heat treatment is complete, the crankshaft falls into the hands of quality control specialists, and here begins the final, most important act in the creation of this giant part. Not only the engine's operation, but also the safety of the entire vessel depends on the accuracy and reliability of these checks. The first step is a visual inspection. Specialists carefully check the shaft's surface for cracks, scratches, defects in painting or coating. For this, they use magnifying glasses and special lighting devices capable of detecting even the smallest irregularities. After all, any microcrack can become a point of failure during operation. Then, ultrasonic scanners are used, which penetrate deep into the metal and detect internal defects, voids, inclusions, stresses in the structure. The crankshaft is wrapped with special sensors, and a computer system reads the signals and creates a 3D map of its internal structure. Next, magnetic particle inspection. This method allows finding the smallest surface cracks that may be invisible to the naked eye. The crankshaft surface is coated with a magnetic powder, and under the influence of a magnetic field, the powder particles gather at the defect sites, clearly highlighting them. Did you know that each year the world faces the challenge of decommissioning millions of old electrical transformers? These metal giants, often found quietly powering our neighborhoods, can hide an incredibly dangerous secret. Many older units are filled with highly toxic chemicals, like deadly PCBs. A single misplaced cut or accidental spill could cause severe, long-lasting environmental damage across vast areas. Taking down these hazardous units isn't a typical scrapyard job. It requires a specialized, highly precise, and incredibly dangerous industrial process happening behind closed doors. Get ready to see the intense operation to safely dismantle these toxic time bombs. So, why exactly are these old transformers so dangerous? For decades, many relied on a coolant liquid called ascarel, which contains polychlorinated biphenyls, or PCBs. These chemicals are terrifyingly persistent in the environment. They don't break down easily, and they are highly toxic to humans and wildlife. Even a small leak from a neglected unit can contaminate soil and water for generations. Modern transformers use safer, non-toxic oils, but the legacy of PCBs in older units means they cannot simply be scrapped like regular metal waste. They demand specialized, heavily regulated facilities designed specifically to handle these hazardous materials with extreme care and containment. The intense process begins when old transformers, often behemoths weighing thousands or even tens of thousands of pounds, arrive at these specialized decommissioning plants. Picture massive yards filled with these silent, potentially hazardous giants, waiting to be processed on a dedicated industrial line. The absolute first step isn't dismantling or cutting. It's meticulous documentation and assessment. Each arriving unit is rigorously inspected, its history and potential contents checked to determine if it likely contains PCBs or other hazardous materials. They are categorized based on size, type, and estimated contamination level. This initial sorting on an industrial scale requires heavy-duty lifting equipment, massive cranes and powerful forklifts, just to move these incredibly heavy pieces of electrical history into position for the next stage. Once identified, categorized, and positioned, the transformers move onto the dedicated high-containment processing lines. The absolute priority here is total containment and zero exposure. Every single step is designed with redundant layers of safety to prevent any spills or contact with the toxic materials inside. Workers operating on these lines are encased head to toe in specialized protective gear. Full chemical suits, filtered respirators, multi-layered gloves. The air quality within the facility is under constant, real-time monitoring. These are not standard factory conditions. They are hazardous material handling zones requiring maximum vigilance. The first critical task on this line is to meticulously drain the internal coolant oil. This oil, especially if it contains PCBs, is the most dangerous component, the liquid heart of the toxic secret. Draining the hazardous oil is a highly precise, high-containment operation, executed with surgical care. Transformers are carefully positioned over multi-layered sealed collection systems, often including large secondary containment basins designed to catch any potential leaks or spills, no matter how small. Workers use specialized pumps, leak-proof fittings, and designated tools to access drain valves and carefully remove every single drop of the hazardous oil directly into secure, heavy-duty, properly labeled tanks. This cannot be rushed. It's a slow, deliberate process. Think of it like disarming a complex device. Every connection, every hose is checked and rechecked multiple times. This step is the most crucial for protecting the environment from widespread contamination and ensuring the immediate safety of the workers directly interacting with the highly toxic liquid hidden within the steel shell. After every drop of oil is confirmed, safely drained and contained, the transformer must be absolutely de-energized and rigorously verified as safe from any residual electrical voltage. Even units that have been disconnected for years can potentially hold a dangerous charge. Highly trained technicians follow strict, multi-step lockout, tagout, and grounding procedures, physically isolating the unit and discharging any potential buildup to ensure no electrical hazard remains before any physical dismantling tools come anywhere near the unit. Safety protocols here are layered and redundant, because any mistake made at this stage carries the risk of severe injury or worse. With all immediate electrical and chemical hazards neutralized, the physical dismantling begins. The process of breaking down the thick steel shell to access the valuable materials and internal components. This is heavy-duty, industrial demolition work requiring powerful tools. Workers use intense plasma cutters that slice through thick steel casings with incredible heat, powerful hydraulic shears that crunch through metal like paper, and heavy-duty saws. The internal components: massive, heavy copper windings, dense steel cores, and various insulation materials are often incredibly weighty and must be carefully lifted out section by section using overhead cranes and specialized rigging. Imagine cutting open a giant, multi-layered steel safe filled with tangled, incredibly dense, and heavy metal structures. It's a loud, sparks-flying process, but it's executed with engineering precision to efficiently separate the different material streams. As the transformer is broken down piece by piece on the dismantling line, the various resulting materials are carefully sorted and separated onto different processing conveyors and areas. Valuable metals like the pure copper windings are isolated into their own stream and sent for high-grade recycling. Steel casings, cores, and other structural steel components are separated for scrap metal recycling. Aluminum parts are directed to their specific recycling stream. But the key challenge, the hazardous legacy, lies with the contaminated materials. Any solid components that came into direct contact with the toxic PCB oil, internal insulation paper, wooden bracing blocks, contaminated gaskets, even metal parts that absorb the chemical, are now classified as hazardous waste themselves. Handling and disposing of this hazardous solid waste requires extreme care and strict protocols. The safely drained PCB oil, the contaminated solid materials, and even the specialized protective gear worn by workers after handling these substances must be meticulously contained, documented, and transported for disposal according to stringent environmental regulations. This often involves complex logistics chains, moving the waste to highly specialized hazardous waste landfills designed to permanently isolate the toxins, or to permitted high-temperature incinerators, specifically designed and certified to safely destroy PCBs at extreme temperatures. It's a costly, complex, and highly regulated part of the process, a hidden necessary step ensuring those dangerous chemicals never re-enter the environment to cause harm. Despite the inherent dangers and complexities, dismantling old transformers represents a vital dual purpose. Primarily, it's about environmental protection and safely eliminating hazardous waste legacy units. But it's also a significant part of the circular economy and resource recovery. Valuable metals like pure copper, steel, and aluminum, weighing thousands of pounds in a single large unit, are recovered and reintroduced into the manufacturing supply chain. This reduces the need for environmentally impactful new mining operations. So, while the drive is safely neutralizing a threat, the process simultaneously recovers significant valuable resources, making it an essential, albeit dangerous, link in the critical lifecycle management of electrical infrastructure. These highly specialized decommissioning facilities are engineering marvels in their own right. They process hundreds, sometimes thousands of transformers each year, ranging from common small pole-mounted units you see everywhere to massive multi-ton substation giants. Each unit processed represents a potential environmental disaster safely averted and a source of valuable industrial materials recovered, all thanks to incredibly precise engineering processes, cutting-edge safety protocols, and the unwavering skill and courage of workers operating daily in a high-risk, high-containment environment. It's a critical industry that literally cleans up dangerous industrial history. So, the next time you see a transformer quietly working, or simply flip a light switch, take a moment to remember the unseen, dangerous, but absolutely essential industrial process happening far from view. The vital work of dismantling old, toxic giants, protecting our environment and communities from hidden chemical threats, and recovering valuable resources for the future. It's a fascinating, high-stakes look into a necessary industry few people ever see. What part of this hazardous but critical process surprised you the most? Let us know in the comments. It all starts deep underground and ends up in your stove. Geologists hunt for gas, drilling rigs pierce the Earth's crust, and an explosive cocktail of gas, oil, and water erupts from the depths. Next, separators that stratify everything down to the last drop. Compressors that push fuel through pipes stretching 300,000 miles. And finally, the gas is cooled to -260 degrees Fahrenheit, turning it into a liquid to be transported across oceans. But how does it not explode? And how is it made safe for your kitchen? Watch and find out how gas really works. It all begins with geologists searching for true treasures underground, natural gas deposits. And no, they don't walk around with shovels. They use seismic waves to understand where gas is hiding beneath the earth. Once a location is found, well drilling begins. Imagine a drilling rig that can reach depths of over 10,000 feet. The well diameter is usually between 8 and 30 inches, and drilling takes weeks. After drilling the well, steel pipes are installed to reinforce the walls and prevent the well from collapsing. Then comes the magic. Under pressure of hundreds or even thousands of pounds per square inch, gas, along with oil, water, and a bunch of impurities, rushes to the surface. For this, special valves, Christmas trees, are used to control the flow and pressure. When gas, oil, and water erupt from the Earth's depths, they resemble a dirty cocktail with millions of particles of sand, salt, and other surprises. To separate this mixture into pure components, engineers use separators. The mixture, under pressure of up to 500 psi, enters the separator through an inlet nozzle. The first task is to reduce the flow velocity so that gravity can take effect. An inlet deflector, a baffle that breaks up the stream and slows down the movement, is used for this. Imagine sharply braking in a car. Heavy particles like sand and clay immediately fall to the bottom, while lighter ones continue to move. In the separator, the mixture separates into 3 layers. The bottom layer, water and sand. These are the heaviest components. Water with salts and fine particles settles first. Oil is lighter than water, but heavier than gas, so it floats in the middle. Methane and other light hydrocarbons rapidly rise to the top. To speed up the process, separators sometimes have inclined plates or cyclone modules installed, which increase the settling area. For example, plates angled at 45 degrees cause oil droplets to coalesce and fall down faster. If oil and water form an emulsion, demulsifiers, chemical substances that break the bond between droplets, are added to the separator. Sometimes, vibrating screens are used to filter sand from the bottom layer. The gas, meanwhile, passes through wire mesh mist eliminators that collect residual liquid droplets. Float level sensors monitor the thickness of the oil and water layers. If there's too much oil, a valve opens and it flows into a collection tank. A gas valve at the top regulates the pressure so that the gas doesn't exit too quickly. The ideal pressure is between 100 and 300 psi for effective separation. A sand dump valve periodically opens to remove sediment from the bottom. A typical vertical separator for gas fields is 20 to 40 feet tall. That's like 2 or 4 giraffes stacked on top of each other. The diameter is 4 or 5 feet, roughly the diameter of a circus ring, and it's capable of processing up to 10,000 barrels per day. A separator is a complex device where physics, chemistry, and mechanics work together to create 3 separate streams. After all, if gas contains liquid droplets, it can damage pipelines through corrosion or hydraulic shock. and 1% water and gas reduces its heating value by 5, or even 7%. That's like adding gasoline to your latte. Oil from the separator is sent to storage tanks, water is purified or re-injected into the formation, and gas heads to dehydration units. Some gas components, propane, butane, ethane, can be separated out. To do this, the gas is cooled to 150 degrees Fahrenheit, and these components condense. They are collected in special tanks and sold separately. For example, propane for grills or butane for lighters. Clean gas isn't ready for its journey yet. It needs to be compressed to a pressure of 800 or even 1,200 psi to be pushed through mainline pipes that stretch for thousands of miles. Compressor stations, true giants with engines producing thousands of horsepower, are used for this. Gas moves through mainline pipelines with diameters ranging from 24 to 48 inches. They run underground at depths of 3 to 6 feet, and their length can reach thousands of miles. Compressor stations are located every 50 to 100 miles to maintain pressure. When more natural gas is extracted than is currently needed, it isn't just vented or left idle. This valuable resource is stored in special underground storage facilities, which can be imagined as huge banks for gas. The most common types of such storage are depleted oil or gas fields, as well as salt caverns, located at depths of up to 3,000 feet underground. Depleted oil fields are cavities left after oil or gas extraction. They have natural geological barriers that prevent gas from escaping. Gas is injected there under pressure through special wells, where it is stored in porous rock, filling the voids previously occupied by oil or water. A single well can produce up to 10 million cubic feet of gas per day. Salt caverns are artificially created cavities in salt formations. They are formed by dissolving salt with underground water, creating large voids that are ideal for gas storage. These caverns have high integrity and allow for rapid injection and withdrawal of gas, making them very effective for regulating supply. Underground gas storage is very important for the stability of the energy system. In winter, when gas consumption increases due to heating, additional gas is withdrawn from these storage facilities to meet consumer needs. Similarly, during peak load periods or emergencies, these underground banks help prevent supply interruptions. Storing gas underground is also economically advantageous, as it allows for balancing production and consumption, reducing costs for surface transportation and storage. It's a reliable and safe way to ensure that gas will always be available when it's needed most. The length of gas pipelines in the United States is over 300,000 miles. Before gas reaches your home, it undergoes another check for purity and pressure. At distribution stations, the pressure is reduced to 0.25 psi, which is safe for home stoves and boilers. For safety, a special odorant, mercaptan, is added so you can detect a gas leak. At all stages, from the well to your kitchen, gas is monitored by pressure, temperature, and composition sensors. In case of an emergency, valves shut off the flow in seconds. Personnel undergo training, and systems automatically record the slightest deviations. Besides homes, gas is supplied to power plants, factories, and chemical plants. For industrial consumers, the pressure and volume are higher. Pipes with diameters up to 48 inches and pressures up to 1,500 psi are used here. Gas can be liquefied. It's cooled and transported by tankers across seas. First, the gas is compressed, meaning it's made very dense, like when you squeeze the air in a balloon. It becomes smaller in volume, but warmer. Then, this warm compressed gas is passed through special coolers. After that, the gas is passed through special devices, expanders, which allow the gas to expand and cool down even more, like when you let air out of a balloon and it becomes cold. Thanks to this, the gas cools down significantly, to about negative 260 degrees Fahrenheit. When gas cools to such a low temperature, it turns into a liquid, like water, but very cold. This liquid gas takes up about 600 times less space than in its gaseous state, so it can easily be stored in special tanks and transported by ships. Imagine this: red-hot metal up to 33 feet long, bending as easily as if it were a sheet of paper. Every year, factories all over the world create millions of parts, from car bodies to giant pipes, thanks to bending machines. But how are perfect bends, channels, and even spiral shapes for oil and gas giants born from cold, formless steel? And how can it be done without wasting tons of energy? Let's dive into a world where metal obeys human will. A bending machine. Think of it like a big construction set for metal. Imagine a flat sheet that needs to be bent into a specific shape. The machine takes this sheet and bends it using special tools to get the desired angle or form. First things first, the metal sheet needs to be checked to make sure it's suitable for the required part. This includes checking dimensions and looking for defects like cracks or breaks. The metal sheet is cleaned of dirt and rust using a wire brush or sandpaper. This is necessary to ensure clear marking and subsequent processing. Markings are applied to the sheet using special tools like rulers, squares, and scribers. The layout includes drawing center lines and contour lines, as well as marking the centers for any future holes in the part. To make sure the markings are clear and don't rub off during processing, the metal surface is coated with a special paint. Dry chalk, a chalk solution with glue, or a copper sulfate solution might be used. After applying the markings, they are checked against the part drawing. In large industrial settings, automated systems are often used to lift and place metal sheets onto the machine. These systems might include conveyor lines and robotic arms that precisely position the metal sheet on the machine's bottom die. In smaller workshops, or during small batch production, metal sheets might be placed manually by workers. Workers in protective suits and gloves lift the sheets using special tools or lifting equipment and place them onto the machine. Metal sheets can vary greatly in size, from small ones easily lifted by hand to enormous ones requiring special lifting equipment. In large industrial settings, you might see sheets up to 33 feet long and up to 10 feet wide. Then, the necessary tools are selected: a punch for the upper part and a die for the lower part. These determine exactly how the metal will bend. During the sheet metal bending process, the machine presses the punch onto the sheet and it bends into the die, forming the required shape. This process allows for creating various shapes and angles, depending on the type of punch and die used. The most common method is V-bending, which is used to create angles of various degrees. This shape is widely used in manufacturing elements for construction, machine, and equipment housings, frames, and so forth. U-bending is used to create U-shaped channels from steel and other metals. This shape is ideal for manufacturing metal profiles and channels. Radius bending is used to make parts with cylindrical or conical configurations. Such shapes are used in the production of pipes, cylinders, and other three-dimensional structures. One variation of polygonal bending used to obtain complex shapes is P-bending. Bending sheet metal allows for creating various shapes and angles, but creating a spiral shape is a more complex process. Spiral forms are usually made using special methods and equipment, such as roll-forming machines. These machines are used to produce cylindrical, conical, and other curved surfaces. They allow for creating spiral shapes by sequentially passing the metal through rollers that gradually form the desired shape. Such machines are widely used in the production of pipes, cylinders, and other metal structures that require a spiral form. While roll-forming machines are operating, you can see how metal sheets pass through the rollers, gradually acquiring the desired spiral shape. Spiral forms are used in various industries and everyday applications. They offer high strength, excellent conductivity, resistance to corrosion, and fatigue. Springs, connectors, heat exchangers, electrical engineering and electronics, the oil and gas industry, chemical processing, and medical instruments all use products with spiral shapes. For example, in beryllium copper spiral tubing, the spiral form is used in 50% of applications due to its high conductivity and strength. Spiral cables are used in over 70% of industrial automation systems because of their flexibility and resistance to mechanical wear. Spiral springs are found in over 30% of mechanical drives due to their ability to provide varying spring forces. Spiral pipes, often referred to as coiled tubing, offer several advantages in the oil and gas industry. They can easily adapt to changes in elevation and direction during the transport of oil and gas. This is particularly important when constructing pipelines in complex geological conditions. Coiled tubing has a spiral seam, which facilitates installation. This can reduce assembly time compared to traditional pipes with straight seams. Coiled tubing is used in well clean-out technology after hydraulic fracturing. Nitrogen is pumped through these tubes to wash out proppant from fractures, which increases maintenance intervals and reduces the time needed to bring the well back into operation. Metal forms can be made from various materials, such as steel, aluminum, or copper. The choice of material depends on the requirements for the product and the possibility of reuse or recycling. Traditional manufacturing methods can involve high energy and resource consumption, which can negatively impact the environment. However, modern technologies, like using renewable energy sources and optimizing production processes, can significantly reduce this impact. Metal forms can be recycled and reused, which reduces waste and the need for virgin materials. This is especially important for steel and aluminum products. To protect metal structures from corrosion, powder coatings are often used. These are more environmentally friendly compared to traditional paints because they do not contain organic solvents or harmful substances. Switching to solar, wind, or hydropower can reduce greenhouse gas emissions by 70 or even 90% compared to traditional energy sources. Improving technological processes and automation can reduce energy consumption by 20 or 30% and cut waste by 25%. Reusing metal forms reduces waste by 50 or even 70%. Every year, over 2 billion cacti are grown around the world. And we are not just talking about your grandma's windowsill plant. They are crushed into cosmetics, tossed into salads, turned into textiles, and even transformed into cactus leather. The largest plantations stretch across thousands of acres in Mexico, Italy, and the United States. These plants grow without a single drop of irrigation, absorb carbon dioxide better than trees, and thrive in places where even weeds seem exhausted. Cacti are charging into the future, and not just in flower pots. In this video, we will show you how they are grown, why the world needs so many cacti, and how they might just help save the planet. In the United States, cacti have long outgrown the souvenir market. They are cultivated for cosmetics, pharmaceuticals, bioleather, livestock feed, and even as an edible superfood. While most people associate cacti with Mexico, it is actually the United States that has become one of the leaders in industrial cactus farming. The United States was not always at the top in this field. Mexico traditionally held that title, where cacti are a national plant, a food source, and a cultural symbol. But starting in the 2000s, when the global boom for superfoods, vegan products, and eco-friendly materials began, American farmers and startups saw a golden opportunity in cactus farming. They figured, quite reasonably, that the climates of Texas, Arizona, and California are ideal for growing prickly pear, nopal, and other species. Plus, the United States has a huge market of consumers seeking healthy, vegan, locally produced goods. So, the demand was already there. Many agricultural startups received grants, investments, or government support to launch sustainable cactus farms. Fast logistics, existing processing infrastructure, and support for small agribusinesses all played a major role. By the 2010s, especially after 2015, farms started popping up not just for food, but for cosmetics, medicine, and leather. And since 2020, when the world embraced alternative materials and zero waste, the United States has stormed into the top producers of cactus-based bioleather. Now, American plantations supply products both domestically and for export to Europe and Asia. The largest plantations are found in Arizona, Texas, California, and New Mexico, regions with dry climates, lots of sun, and very little rain. In Maricopa County, for example, cacti are cultivated across dozens of acres of open land. The main variety here is prickly pear, prized for its fast growth, edible fruits, and industrial applications. It all starts by selecting the hardiest, most productive cacti, those that have shown strong resistance and consistent yields. For instance, a single prickly pear plant can produce 20 to 30 fruits in one season. Farmers cut a segment from the parent plant, usually one pad or shoot, and dry it for 3 to 10 days so the cut seals and does not rot in the soil. These cuttings are then planted in a sandy clay substrate, sometimes directly in open fields, sometimes in containers for rooting. The rows are spaced 3 to 5 feet apart to allow equipment access and minimize light competition. Cacti take 3 to 4 weeks to root, and the first fruits or shoots appear after 6 to 12 months, depending on the variety and climate. During that time, farmers monitor humidity and temperature. Once the first plants are well established, the farm expands by taking new cuttings from these fresh plants. This creates a stable, nearly self-sustaining system. So, it all begins with one spiky stalk, and within a year, it can produce dozens of new ones. To keep a cactus field looking like a postcard-worthy Mexican paradise, it needs real maintenance. Sure, cacti are desert survivors, but once you grow them by the ton, they become a little more delicate than the ones on your windowsill. On a commercial scale, drip irrigation is used, a system of tubes that slowly but steadily waters each plant. The average is 4 to 8 gallons per plant per week, depending on the climate. Next comes pest protection. The biggest threat is not rain, but cochineal. This fuzzy white bug looks like a cute puffball, but drains the sap out of plants faster than you chug a smoothie on a hot day. Then there are spider mites, nematodes, and other microscopic monsters. What do farmers do? They use biocontrol. They release predatory insects to hunt down the pests. It is like Game of Thrones, in bug form. Sometimes they also use natural insecticides, like garlic-based sprays or neem oil. Cacti prefer nutrient-poor soils, but a little boost never hurts. Once a season, farmers add compost or a special blend of nitrogen, potassium, and phosphorus. It is all done by the book, between 11 and 22 pounds of fertilizer per acre. Otherwise, you will end up with a jungle, not a farm. Harvesting on large cactus plantations is not some old guy with a machete. It is a full-blown operation. Harvest usually happens in the morning, before the sun turns the fields into a frying pan. Workers wear protective gear, because those spines are no joke. They trim ripe fruits or pads with special knives, or even mechanized tools. One person can harvest between 1,000 and 1,500 pounds of raw material a day. And if the farm is automated, that number can double. The most popular varieties, nopales and tuna, go on to be sorted. Each plant gets inspected: size, weight, color, and damage. Some fruits are automatically weighed, scanned, and sent down a conveyor. Premium ones head to supermarkets. The rest go to processing or canning. Workers manually inspect up to 1,000 units per hour, so the concentration level is like the final scene of a TV drama. The biggest farms use computer vision systems that sort out defects and count yields. Sorted cacti are packed into boxes or plastic crates, labeled and prepped for shipping. Shipping cacti is all about delicacy and timing. Packed in ventilated containers, they are loaded into refrigerated trucks. The temperature stays between 40 and 50 degrees Fahrenheit to prevent the cacti from turning into mush. On average, one truck carries about 40,000 pounds of product. If it is for export, cacti may travel thousands of miles to Europe, Canada, or Japan. To keep everything fresh, logistics must be timed down to the minute. And a little bit of luck helps. No one wants to open a box of shredded, spiky bits instead of bright green segments. Young prickly pear pads are no longer exotic. In major supermarkets in California, Texas, and Arizona, nopales sit right next to broccoli and romaine lettuce. And yes, they go on sale on Fridays. They are often sold pre-cleaned and sliced into strips, cubes, or thin rounds, or pickled in jars with peppers, garlic, and onions, basically like Mexican pickles. Nopal juice or powder is added to smoothies and supplements. It is good for digestion, helps manage blood sugar, and is considered a superfood. Fried with eggs, cactus is a classic breakfast dish. Think of it like Mexican scrambled eggs with a tangy green twist. It also goes in tacos and burritos, adding texture and a slightly slimy but pleasant acidity. Prickly pear tastes great in salads with tomatoes, feta cheese, peppers, and cilantro. It is also baked with cheese or meat as a side dish, or turned into cactus lasagna. The taste? Well, it is an acquired one. A bit like green bell pepper, a bit like beans, with a slight tang and a slippery texture. If you do not roast it well. But once you try it, you often come back. Do you like the taste of nopal? Share your favorite recipes. If you think cacti are just about spines and sand, you're missing the big picture. They store water in their stems for years. Like real soil-based banks, they hold reserves for hard times. In deserts, they become water distributors for entire ecosystems. Nopal, like many other cacti, is also used in folk medicine for treating everything from diabetes to digestive issues. Its gel helps heal wounds and prevents scarring. In some countries, cactus-based cosmetics are common. Nopal gel is often found in moisturizing creams and serums. Its texture allows it to penetrate the skin quickly without leaving a greasy residue. It is known that nopal extract has a calming effect, helping reduce inflammation from sunburns or skin irritation. The oil extracted from cactus seeds, especially prickly pear seeds, has become a star ingredient in cosmetics. Rich in fatty acids and vitamin E, it is a powerful antioxidant. Prickly pear seed oil helps reduce wrinkles and improve skin elasticity. It also soothes and nourishes the skin, preventing dryness. That is why it is often added to eye creams, where it helps reduce dark circles and puffiness. Cactus extracts are also used in hair products. The oil and nutrients help strengthen hair, add shine, and improve scalp health. They may reduce hair loss and stimulate growth while moisturizing dry scalps. Some cactus-based products even offer UV protection. Extracts can form a natural barrier against the sun's harmful rays, helping prevent sunburn and irritation. Brands like Kiehl's, Fresh, and Herbivore Botanicals already use cactus extracts in their products. Facial creams, serums, shampoos, and hair masks featuring cactus are especially popular. Nopales can live for decades. Some cactus species even live for centuries. For example, the saguaro, the giant cactus, can live up to 200 years and grow to 40 feet tall. That is about 1 inch of growth every year. And it is not just the stems that are edible, the flowers are too. Prickly pear flowers, which often bloom red or orange, can be tossed into salads, brewed as tea, or used as edible decorations on dishes.